smart robotic to assist people, especially in health. And his research is excellent, can be evidenced by publication in Nature and Science Robotics and TRO, or all these are top journals. And I hope today you will talk about your research in Nature. And also he has received many national rewards, including ESF Career Reward and Victor Distinguished Fellowship, and also Two-Time Mobility Change Discovery Award, many awards. So, very look forward to your talk, and thank you very much for visiting us, and all yours.
Yeah, thank you. Yeah, thank you. Thank you for the kind introduction. It's a great honor to be here today. Like I really appreciate the opportunity to visit the Purdue, and really thanks for the organizer, the leadership, Dr. Mo, and and also Richard and some of my friends, like helping me and for my career. Here, like when I was student, when I was college student, when I did my PhD application, Purdue is one of the handful university. I decided to apply without checking US news. Really honored to visit you today, and thank you for this opportunity. In our lab, we focus on design, learning, and control with application in healthcare. In particular for rehabilitation through exoskeleton, robotic systems, and a surgical robot for minimally invasive surgery. So for this talk, I will focus on this kind of like robotic application in healthcare, and with special emphasis on how we design high-torque motors and do reinforcement learning in simulation. This kind of like two major research areas. In our lab, we develop AI-powered mechatronics and robotic system that span the continuum care, ranging from disease prevention. We designed some like a soft back axial suit to prevent musculoskeletal injury. We also designed a mechatronic system for ultrasound guided wearable robot, like a snake that can do deep dive inside a human lung for early lung cancer detection. About 12 years ago, I also worked on some like MRI compatible robot. Nowadays, we still work on neurosurgical robot, but using X3 as guidance. Basically those image compatible robotic systems. In the last about 8 to 10 years, we have been focusing on exoskeleton, including lower limb exoskeleton to improve mobility. This one published in Nature last year from my lab. We also develop upper limb soft exosuit and soft exoskeleton. So both soft robot and compliant robots to improve manipulation for the upper limb. We also designed some like actually my background is mechatronics. We do a lot of design, but we also do learning and control. So we designed some like a transcutaneous simulator, some electronic stuff, and also some robotic prosthesis, like an exoskeleton and the prosthesis, this kind of wearable robots. For today's talk, I probably want to give you a big picture about our research. If we look at robotic exoskeleton and prosthesis through the lens of design. If you look at the vertical axis, if I play this video again, you probably can see this industrial robots are really they're not lightweight, they're not compliant. Many exoskeleton systems like this one, actually the underlying design principle is very similar to this. So overall, they are pretty heavy and not compliant, very stiff, and overall not very safe, right? So our overall goal is to design robots that can be very lightweight through mechatronic design. So basically design the electronics, design the actuator, and overall mechanism design. One key objective is to reduce metabolic costs, basically reduce the energetics during human locomotion or during human manipulation. So this you can see this evolution, our lower limb exoskeleton and upper limb exoskeleton. The overall goal is to actually not only to reduce the energetics, but overall make that lightweight, compliant, so people feel that they're really comfortable. People are really willing to wear this kind of robotic system. If you look at our research through the lens of control, why we need control, why we need learning this kind of solutions. maybe look at the horizontal axis, you can see many robotic systems. If you watch the video, you can see they are not very natural, not very fluid movement. It's more like a robotic system, right? More like a robot movie. The reason is that it's a robot that initially control, so it's the kind of like a robot forcing the person to walk, right? And the second aspect is typically it can only affect the walking or running, single locomotion activity, right? In particular, on a treadmill, this kind of like a steady state walking or running, right? So it's not walking and running, it's walking or running, this kind of like a single activity assistance, right? So our overall goal to come up with a new control and the learning paradigm to make the robot truly versatile, right? Because for human, we don't only do walking only. Even you do walking, you do a different kind of crazy walking patterns, right? So we want the robot truly versatile and can really help people not only on the treadmill setting, but on in daily activity living, for example, and in home or in community settings, right? For today's talk, I will cover 3 aspects. The first part is kind of like focus on our key expertise in design, mechatronic design. The second part, I will cover how we do autonomous control, how to make the robot truly more intelligent, so we can offload the effort by physical therapists, right? Make the robot easier to use for therapists and also for the end user. The third part, I will talk about some of our work on surgical robotics. They carry similar theme in terms of how to make the robot really compact, portable, and efficient in terms of mechatronic design. But in addition to this, we try to make the robot ultra steerable, super dexterous, so they can go dive deep inside the human lung or go inside the human brain. This is a very complicated anatomical structure. If we start from this exoskeleton design, I will first talk about our bio-inspired actuator. Then I will go through how we come from the actuator level to robotic level, right? So maybe you can see this video on the left video first. In some sense, we take a walking or locomotion for granted, right? So why making exoskeleton is difficult, right? So if you look at the right side of this, it can tell actually for a single limb, they require 9 muscles to control the body, right? So you put hand up the left and right limb together, 18 muscles, right? To control both the timing and the magnitude, right? Timing and magnitude for 18 muscle groups, right? So that's not trivial work. And on top of this, there's larger variability, right? From person A to person B, almost no one walks the same way, right? Because larger variability across humans, right? So this 18 muscle coordinated control, whether we add a robot, we really should understand human intention, right? I think maybe more importantly, I would say, really for research, it's not only solving the problem, but really think about what's the most important problem to solve, identify the need, right? Identify what problem to solve is also maybe in some sense is more important. I heard one professor from Harvard recently said, you probably think most professors every day think a lot of crazy ideas, But he said it's not really a lot of ideas. The idea is to get rid of not important, low priority ideas, right? So really decide what's the high impact research, high impact problem, I think important. In our case, we truly want to really understand the human biomechanics, but on top of this, we really want to understand the needs of physical therapists, or the needs of the people with disability, or even older adults, even people like you. We can use exoskeleton for hiking, right? So really want to understand the human, really understand the overall control or design challenges in the real world, right? Not only so really understand human. This we call this use-inspired basic research, right? Really makes that practical and useful. If you look at the video on the right, you probably can tell here. If you see the video again, is it you probably can tell this actuator is doing some jerky motion, right? Though overall, you can probably get some sense about skeletons are very heavy, bulky, right? So that's one limitation. The second part is when the person walks here, you see the robot doesn't really synchronize with humans very well, right? So it suddenly has this kind of like a jerky motion. That's something like because of the discrete control, and also overall, our goal is to really understand human intention, synchronize the robot with humans, right? So really kind of like a human intention first, to detect this and follow humans, and forcing humans to walk, right? So you probably can sense this kind of control is not easy, right? Also design is challenging, right? Go back to the use-inspired basic research. Even for walking, we look into the walking biomechanics. We came up with this bio-inspired actuator design. If we look at the human biomechanics, one important feature is that normally human locomotion has high torque, right? Around like 120 Newton meter. But the speed is not a super high speed at like a machinery, but it's not too slow, right? So overall, like a really high torque requirement. For conventional motor, most conventional motor can really only provide a very kind of 0.5 Newton meter, kind of small torque. Even you get like a bulky motor like this size, is actually the torque level is pretty small compared with the required torque capability for a human, right? Even if we provide 30 to 50% biological assistance, let's say 15 Newton meter or 60 Newton meter, this kind of like a partial assistance, because our idea is not to provide 100% biological assistance. We don't want to completely replace human effort, right? We want it to be assistive, right? So our robot, we call this assistive robot. We don't call it a rehab robot. It's not a rehabilitation robot because it's assistive. It provides partial assistance. So it's kind of like basically the robot does let's say 30 to 50%. Human, you still need to work, right? You cannot completely rely on the robot. So that's our overall design philosophy. But even in terms of this, right, another torque capability of a standard motor is still very limited, right? And the conventional motor is generally very high speed, right? So when I started my faculty position, I said, oh, what's the research area we should focus on? Should we do EMG-based control, or should we start from actuator? So when I watched the talk by Steve Jobs, he said, people who are really serious about the software should make their own hardware. Okay, I realized, okay, maybe probably we want to start working on actuator first, right? So it turned out to be actually a very important researcher problem now. But you know, maybe 10 years ago, people don't were not aware of this. You know, this is a big limitation. For example, if we take an anatomy of a standard exoskeleton, it consists of electric motor, usually low torque, high speed. High speed is a bad thing, right, for human. And low torque is also kind of bad feature, right? That's undesirable, right? And because it's low torque, it requires high ratio gear mechanism to amplify the torque, right? So that's why a lot of harmonic drive mechanism from 100 to 1 to 200 to 1 is very bulky, very expensive, and it's $1,000 price for this, even the harmonic drive. This is a harmonic drive. It's actually very bulky transmission mechanism, right? So our idea is to provide partial assistance and using high torque motor and some like a soft transmission, could be cable, like when I say soft execute, typically it's based on the cable fabric, like a soft actuator solution, or even elastomer, right? So we have actually purely a motor and a gear solution, and also motor gear with this kind of like a software transmission. We call this exosuit solution or exoskeleton solution, right? So overall, if we think about any robotic system that will collaborate with human, there are those like 4 metrics, right? Compliance, bandwidth, efficiency, and the cost, right? So if we look at the standard industrial arm, overall, they have very mediocre compliance. They are very stiff. They are unsafe to work with the human. Overall bandwidth, they're pretty excellent and have also a pretty mediocre efficiency, because another drawback of high ratio transmission is not only the system is very stiff. The second drawback is that it typically has a very low efficiency, because of the high, you probably need 2 stages or 3 stages for the gear transmission, right? So overall efficiency is also not desirable. If you look at a series elastic actuator, this is still some kind of like still very popular. If you check TRO, people still publish this, this kind of, SEA type actuator. So the idea is kind of very simple, right? Because we know for the first actuation, compliance is the major limitation. So people added a mechanical spring. This is, I think, maybe start from MIT around 25 or 30 years ago. They added mechanical spring to embody some like compliance to the robotic system. But overall, you say they are still very similar. The efficiency, in some sense, is maybe even worse because of the gear transmission, the spring transmission, and also overall still very low efficiency, because they still rely on this high ratio transmission mechanism, right? So in our lab, we work on the exoskeleton. We call this quasi direct drive, QDD. The general idea actually, had been there maybe 20, 30 years ago from haptics community, right? The general idea, but it was not possible until about maybe 10 years ago when MIT Cheetah, right? The Sam Kim, he started doing the humanoid robot, and this quasi direct drive actuation getting popular. But for exoskeleton, for medical robot, right? For leg robot, they don't really work with human directly. It's not physically coupled with human like an exoskeleton, right? And also the overall dynamics is still very different, right? So it has a very different design requirement. Most importantly, for exoskeleton or surgical robot, there's always a human in the system, right? So that's the human is always the difficult part, right? So how can we leverage quasi direct drive? This kind of like a little bit kind of a traditional idea, really give this kind of new blood, new solution to exoskeleton. I think even nowadays still kind of like not a well-studied research area, right? So overall, we wanted to improve compliance, bandwidth, efficiency, and even reduce the cost. I think the key feature is that it rely on this low ratio transmission gear, right? But you probably can realize there's no free lunch, right? How can we optimize everything? What we have to compromise? I think the cost is how to design high torque density motor, right? So this is not quite straightforward, right? So in my lab, we have been working on electric motor, basically the standard BLDC. I mean, it's standard in terms of the general category, but one key key result we found that in our this kind of TMAC paper, actually transaction on electronic paper, we published about 5 years ago. We found that this kind of pancake motor is better than this. This is a pancake motor, right? Than this kind of like a sausage type of motor, right? So in terms of geometry or topology, this pancake motor is better. In our paper, we also found that this is called interior rotor. So basically, the rotor is inside, right? And the second topology is the interior rotor, also called a runner, outer runner rotor. So this one is better in terms of top density, right? We call this bio-inspired because it's not based on the biological system, but this because human we need a higher torque and a lower speed compared with the traditional motor design, right? So we want to do this kind of like a high torque and high torque density design. So we found that this outer runner motor is better. So this is something very, very important result. Recently, we also we are still working on the new generation of robotic design. Another important finding we identified is that actually we don't need a really high torque, right? So 18 Newton meter is good enough. Actually, for most people, they feel like a 10 Newton meter is already a lot of torque, right? So if I put an exoskeleton on you, 10 Newton meter, you probably don't want me to apply 18 Newton meter, but we intentionally make that a little bit higher than maybe average, to cover more population. So that actually this is very, very important because many groups or even some companies, they do 30 Newton meter. That's actually very, very large torque, and I consider that's unnecessary, right? It's a heavier, larger, but it's more expensive. But we found that 18 Newton meter is good enough. Actually more than sufficient, right? So for those two motors, right, they have similar torque ability, but we further reduce the thickness and the weight, right? Because as I keep saying, it's use inspired because we found that no one wants to wear a heavy and bulky motor, right? So we keep pushing the boundary of the mechatronic design through the actuator design. On top of the actuator design, you probably realize for any robotic system, it's not only the actuator, right? On top of the actuator, there's this electronics, in particular mechanical design, right? On top of the, even let's say, if I give you actuator, we need to design this kind of like a variable structure. For this, for example, this is side brace, right? So from this picture, you probably can see our overall design goal is to reduce the overall mass through the mechanical design and also through the actuator design. And also we identify that 18 Newton meter is kind of like really ideal torque level, at least for the hip joint and even the knee joint, right? Even I think for the ankle joint, there's a sufficient torque capability. And we were able to reduce about 24% energetics during human locomotion, during walking. You can see the key idea is, as I said, it's the actuator design, right? This is the first element. The second element is a simple mechanical design. So overall, our design is very, very simple. We don't want to do some very complicated mechanical design. So this is kind of like our V3, our last version. This is our latest version, right? So you can tell, the actuator is around here, right? The actuator is getting smaller. The overall mechanical design, the mechanism, right, is also getting smaller. The third part is also the electronics, right? Initially, our electronics is like this size. Our current electronics is roughly 50% smaller. So overall, this is getting close to some like consumer electronics grade exoskeleton. So overall, it's a pretty compact, can deliver actually very high torque. Most people don't want to get up to 18 Newton meter, right? 10 is that's too painful to go to 18 Newton meter, right? So this is kind of like we call this exoskeleton because it's compliant, but not really soft, right? We don't really use much soft material, and it also can support multiple activity, right? Many exoskeleton can only help people to walk, right? But for our system, we want the person to walk, run, and squatting, and do a lot of crazy activities, right? If we think about the mechanism design, right? So my own background is not only actuator, but also the mechanism design. So for rigid exoskeleton, there's some like limitation. There's pros and cons for rigid exoskeleton. For soft exosuit, there's also pros and cons. For example, for the exosuit here, because the movement arm is very short here, right? So you can tell, for example, the movement arm for this limb, right? It's this long. It's almost like your limb length, right? Here is only the radius of the limb, right? So the movement arm is getting much smaller. But we want to generate the same amount of torque, right? By doing this, you have to generate a really high force, right? So movement arm small, the force need to be larger, right? So simple, mechanics, but that means you need to generate the actuator. You need to generate 700 Newton. That's basically like a weight of person, right? That's really, really high force. Think about it, we are doing this portable actuator design. So when I wear this, it's very, very hot. It's really, even in Boston, even in winter, it's a super hot, need a lot of like a cooling system, right? And even for human, this is we don't like a large shear force, right? We don't like this kind of shear force along the limbs, right? There's always pros and cons for each solution. So our system is not perfect, but we try to combine the best of those two worlds, right? For example, we have this cable transmission. This is idea borrowed from soft exosuit, but in the distal portion, it's kind of like a rigid exoskeleton solution, right? More like the traditional. So we call this hybrid exosuit design. So it has a smaller shear force and a larger moment arm. So it basically feels more comfortable to wear this kind of hybrid system. We also work on some knee exoskeleton. For example, this is a spin-off company from Google. Their system is about, I think overall very nice. Because we focus on actuator design, we are very fortunate to be able to reduce the overall mass to about 2.3 kilograms. In addition to mechatronic design, we do a lot of human experiments, right? We work with leading rehabilitation hospitals and to test our robots for people with stroke, spinal cord injury, neurological impairments. And we also test this on people with arthritis. This is kind of like a musculoskeletal impairments.
With the Zod, it actually helped me. I felt that I had more stability, it helped my balance, and my gait kind of went very natural. I felt very comfortable in the sense of, wow, this is going to be my friend.
I love it. It took about, a minute because it's pretty easy. I'm walking a lot lighter. It's very low profile. I don't hear noise when I'm walking. Everyday use, this is perfect.
They have to tell us what they need. They have to tell us what they want so that when we finalize the soft exoskeleton, it is something that will be useful, meaningful, something that will help them in their recovery and their activities of daily living.
With the Zod.
Yeah, so as I mentioned, we most exoskeleton is for neurological rehabilitation, right? For people with a stroke, basically with some brain impairment, with a stroke or spinal cord injury. So we tried our robot, basically tailored it, reduce the, makes that more suitable for people with knee arthritis. Overall, people with musculoskeletal impairments is a much larger population. But overall, they don't need an exoskeleton as much as people with neurological because their gait impairment is not that severe. So basically, we have to make the robot smaller and more lightweight to really make sure the benefit can really outweigh the kind of like the penalty, because any exoskeleton, there's some kind of mass, right? So people overall, you probably don't want to wear exoskeleton unless the robot really does something really bring extra benefit, right? So with our exoskeleton, we were able to reduce pain significantly for walking, stair climbing, and sit to stand. We extended the same design principle for upper limb exoskeleton or exosuit. So this is also this hybrid exosuit design. You can see there's a portable actuator, cable transmission, and the distal portion is kind of like more or less the rigid structure. But actually, we call this rigid. Actually, it's still kind of like a 3D printed and brace, 3D printed brace structure. So it's kind of very standard in terms of orthosis, right? So in this sense, it's kind of a good feature because we don't want to design our own orthosis, right? We want to do something very standard, easy to use. Overall, if you think about the design objectives or any upper or lower limb exoskeleton, we want the robot to be portable, right? This is only upper limb, but many upper limb exoskeletons or even lower, fully tethered, right, based on the frame. And this is the first design objective. The second design objective is we don't want to impose any restriction on the natural range of motion, right? Honestly, when you wear any exoskeleton, it imposes some kind of like a range of motion limitation, right? So we want to minimize this, right? Overall, exoskeleton is designed to help people, but many exoskeleton, when you wear this, you don't feel super comfortable, right? So in some sense, it restricts natural range of motion. So we want to optimize both portability and unlimited range of motion, right?
Yeah.
Maybe you can feel the difference, like right.
I
feel it.
Yeah. You feel it?
Yeah. Doing some extras.
Oh, this is such a lifesaver. I mean, this is literally making the pressure is like completely lifted, guys.
Yeah, so basically, I mean, where this is actually very interesting. I feel like really someone really helping you to lift up, right? For robotics, right? It's sometimes we call embodied AI, right? So it's not only hardware, right? We also need to come up with some really like a useful software or controller, right? So sometimes I tell my student we want to because my background initially was on mechatronics, right? We said, okay, let's have the best mechatronics, the best hardware, and you know, second grade OK level software, then we are the best, right? But honestly, when we published the paper in Nature last year, we really have the one of the best control algorithm to enable autonomous control of exoskeleton. So simulation is kind of like a digital twin, but for us, it's kind of closed loop for digital twin, right? That's why we call this learning in simulation, right? It's not only building a digital twin of human, but how we learn this control policy in computer simulation is something very new. For any wearable robotics, there are normally kind of like three phases. The first one, you need to do activity classification, right? So you need to classify the person's activity to discrete movement types. The second stage is to do phase estimation, gate phase estimation, like those kind of 4 phases in a single walking cycle called a stride, right? After these 2 phases, you need to come up some like a handcrafted control rule. And for single activity, you probably have like 4 parameters. If you are doing multiple activity, there are hundreds of parameters. Both the researcher need to tune this, and the end user, like a therapist, need to tune this. I think in some sense, why don't we use machine learning, right? So machine learning is popular nowadays, but it was not super popular a couple years ago, even 5 years ago in wearable robotics. It's still very rare. The general idea is kind of simple, right? We don't want this kind of like a handcrafted control. We want this continuous control, right? You know, the robot can do this end-to-end activity classification. So we want to get rid of this kind of like 2 phases scenario, right? So the idea, the overall goal is kind of simple, right? Everyone probably want to do this. Everyone have the similar, maybe it's a similar idea, but how we can really do this, right? You know, the design objective is kind of simple, right? How we can really do this, right? So if you think about the deep learning formula, right? There's neural networks, neural nets, data science, and computing, right? For exoskeleton, which is the most difficult part? Which is most difficult? This first, second? Anyone? Second, why is difficult? Yeah, so I agree with you. I think the data is the most difficult, right? Because how can you know, if you ask the animal does the exoskeleton, you need to do tons of experiments, right? Even let's forget about the exoskeleton, those medical robots, because there's always the human, right? Let's even think about the robot arm. That's also very difficult to get a data set, right? So for example, like an ImageNet, you know, you probably have hundreds, maybe thousands of photos in your smartphone, right? How many robot data do you have in your phone? Right? Probably 0. I probably don't have any, right? So for medical robots, this is extremely difficult. For robotic overall, it's difficult. For medical robots, it's even more challenging, right? But for this neural network architecture is also not very trivial. For example, our solution is based on the deep neural nets, right? And you know, it's kind of standard deep neural nets. How many parameters in there? Do you have idea? How many parameters? Right, let's see. 100, 128 and 60, roughly speaking.
Maybe 500.
500? No, if you multiply this, it's not more than 500. We also have this input layer and output layer, right? So overall, it's about a 10K parameter, right? And we have actor critic is a 20K, even for single network, right? So it's not easy to to get this data to support this training, learn those hyperparameters, right? If we come back to exoskeleton, the general scenario is you need at least a half an hour. This is in the research lab, right? You work with your professor, do this for half an hour for each person, half an hour at least, right? And you need to do this for me for 30 people, right? I think maybe young students have been doing this, right? 30 minutes and 30 people, right? When you do the deployment, right? If an end user wear this exoskeleton, it needs another maybe 1 hour to keep optimizing the control policy, right? Not really a control policy, just some whatever controller, right? So that's this kind of like a human-based solution, right? So we came up with this kind of like a new idea, experiment-free approach. So we don't do any experiments with human or robot. We do everything in computer simulation, right? And GPU is not super cheap, but for us, it's cheaper than testing 30 people, right? So for us, we don't need the high-end GPU. So when we do the deployment, it can be basically zero shot learning can be deployed immediately, right? So I think when I told our collaborators, they said, "Oh, how this is not possible? This you're bluffing. This is not possible." About 5 or 6 years ago, there are a lot of machine learning methods. Why? But we use the reinforced learning. But the key difference with this kind of AlphaGo or ChatGPT, I think most of you probably know, they are based on reinforced learning, right? But they don't need to consider the physical system, right? And in our new framework, we call this model-based, because in the simulation, we simulated the human, simulated the robot, and simulated the human-robot interaction, right? Those three components, they're all model-based, right? There's a lot of like a muscle model or human musculoskeletal system model. And it's also data-driven, right? And in this data-driven system, there are 3 big neural nets to be learned, right? I think that the nice feature about this is they're all physically meaningful, right? So the first column and the second column, they both take place in computer simulation, right? This is a simulator part, this is a learning block, right? So for the first part, right, you have the human, for example, the human kinematics, the human joint angle as the input, right? And it outputs the first part, and then the inverse dynamics, right? From the kinematics to joint torque, right? So this is the first neural network. The second neural network is basically from joint torque mapping to muscle activation to control this virtual human, right? So under this two, you can consider there's no any robot, right? Only the virtual human, and basically how to actuate this virtual human, right? Through the reinforcement learning. And we didn't use the imitation learning because I mean, this is a little bit like imitation learning, but overall it's overall architecture is reinforcement learning, right? And the third part is the controller network, right? So this is the controller of the robot, right? So we learn this controller policy and those two like a motion imitation network and the muscle network, those 3 networks simultaneously in computer, right? And we can, after we learn this control policy, we can deploy this to a microcontroller immediately, right? So this one and this one, they are identical, right? Several researcher questions we kind of like tackled in this process is how accurate the simulator should be, right? We found that actually a simple about 200 muscle for both lower limb and upper limb is ideal. Even our robot is only lower limb exoskeleton. So in the computer simulation, it took about 8 hours. for the virtual human to figure out how to walk, and the virtual robot figure out how to coordinate that with the human, right? Then we can deploy this.
Our train controller
we
could
were able
also produce smooth and continuous assistance for the
24%
three
energy,
activities and especially their
during
transitions
walking,
without the need for discrete activity
13%
classification
during
or gate
running,
phase segmentation.
and 15% during
The assistance profile exhibited distinct shapes for each activity, highlighting its ability to adapt to the changing requirements of the wearer automatically.
No axle condition, right? The black is no axle. If we compare with the assist off, this is the
Proller could also produce smooth and continuous assistance for the three activities and especially their transitions, without the need for discrete activity classification or gate phase segmentation.
Metabolic cost reduction.
The assistance
right?
profile
Because
exhibited
compare with,
distinct shapes for
no
each
axle,
activity,
because,
highlighting its
that's the
ability to
baseline
adapt to the
condition,
changing
right?
requirements.
This is a cover we initially sent to nature. And there's a media like a art illustrator. They said how you need to pay us and do the art work. And nature will probably very soon to hire us to do this. Then we did a couple iterations of this cover. And this is what we sent to nature. We said, okay, hopefully take it. But in the end, they took this one. Do you know what's this? Last year was a Nobel Prize. AlphaFold, right? This is AlphaFold 3, I think, right? AlphaFold, yeah, this is AlphaFold 3, yeah. So yeah, this is the AlphaFold 3, and this yeah, so we are here, artificial assistants here. So not too bad, right? Yeah. Yeah. So overall, I talked about this exoskeleton work, and I also maybe share with you our research on surgical robots, right? Overall, as I said, it's similar underlying design principle to make the robot really compact and portable, and also ultra steerable. This is something kind of new compared with exoskeleton, right? We focus on cardiac and neural intervention. As a surgical robotic researcher, if you ask me what's the next big thing in robot-assisted surgery, I would say one big trend is microsurgery. For example, for Da Vinci assisted surgical system, the incision is about 1 centimeter. We want to come up about 1 millimeter, 2 millimeter, up to 3 millimeter. This kind of small incisions, right? So microsurgery is one big trend. The second big trend is the digital surgery, right? Better imaging, learning simulation, digital twin, and the situational awareness, right? Yeah, we initially work on this MRI compatible robot. The key features compared with Da Vinci surgical robot is that we can use, we developed this MRI compatible actuator based on piezoelectric actuation. And also the robot is kind of like a snake type of robot, right? So it's a steerable catheter, this kind of dexterous needle type instrument. But the overall, I think the overall opportunity is that many robotic systems, right, they are still based on rigid instrument, right? So if you look at the vertical axis, they are based on rigid instrument, right? And overall, they are still kind of like a larger incision, right? So I consider the new opportunity is a flexible, steerable instrument, robotic instrument, but a smaller, right? This is still kind of like an open space in that area, right? For example, we focus on endovascular application. For this robot, our robot, it can go through the femoral artery, go inside a human heart or human brain to remove, for example, blood clots. It's called a mechanical thrombectomy with this catheter robot, right? And it's much smaller than kind of like a standard robot. This is kind of like a Siemens robot. It's a pretty bulky system. Our system is about 20% size of their robotic system. The second feature is that most surgical robots, they are called capital equipment. Normally they sell for $500,000. So we want this to be much more affordable. Also, we want this to be able to handle multiple instruments, right? This one robot we designed. Yeah, we designed this robotic system. to do cardiac intervention and the neural intervention, because for that similar robot, it's only designed for heart. But you can imagine the vessel, neuromuscular vessel is much smaller than cardiac. The cardiac is like a couple centimeter, but this is very small, like a millimeter level, right? So we came up with this really clever mechanical design to make the overall motor much smaller, and also the robot itself is also much smaller. And this is our second generation of the robot. We call this Lego type modular catheter because for example, for cardiac intervention, for some procedure, we only need 2 catheters, right? One catheter does rotation and insertion, and the 2, right? You only need 2 instruments, right? For the neural, we probably need 3. So the solution is simple. Then you just add 1 more catheter, right? But the standard solution is for cardiac, you need to buy 1 robot, right? That's $500,000. Then for the neural, you need to buy another robot. That's another $500,000. Together, you need to buy $1 million, 2 robotic system. So basically, we want to do 1 robot for multiple endovascular procedures. So this is another 1 robot for 2 procedures, but this is a different procedure. The first one I mentioned is basically through the blood vessel, right? Called endovascular. The second one is called endoscopic. So basically, camera-based. It can go inside the human brain, right, through the skull or through the nose, called the transnasal surgery. And overall, it has a kind of like two arms. It's kind of bimanual dexterous manipulation, right? So what's new, right? It's not only 1 robot for 2 procedures. That's a new feature. The second new part is compact, right? This is kind of standard, like a Da Vinci type of surgical robot. If it go inside human brain, that's the scale, right? Do you want the left robot or the right robot? For yourself. Maybe for yourself, maybe you want the right one because smaller, right? Overall smaller robot, and also we call this ultra steerable because it has a really larger bending angle and a smaller bending radius, right? You really want the robot have the capability to do deep dive inside a human brain or heart or even lung, right? So this kind of like a deep dive system. Another feature I want to highlight is that this is a standard endoscopic intervention. So basically, it's an analogy, right? So the endoscope is like a human eyes, right? And about the standard instrument is like a knife, right? So they are coupled motion, right? They are not, not easy to use, right? Not intuitive and the long learning curve, right? That's very difficult to operate this, right? Ideally, you want the robot to have the bimanual, right? And you have 2 manipulator. I'm talking about the catheter, right? And also you have the stereo vision, like a human brain, right? And the motion, they are fully decoupled, like what you do every day, right? So this kind of scenario, right? So this is like a dual arm manipulation with our catheter robot, right? So the catheter is about a 3-4 millimeter diameter. So it's kind of a smaller, small instrument, and also this is the stereo camera, right? In addition to mechatronic design, for the machine learning part, I think there's also great opportunity. Actually, this is still very new for surgical robots, any learning algorithm, because most solution is based on model-based, right? Classical control for surgical robots, significantly behind, like the robotic community or the AI. So some groups work on the imitation learning. For us, we consider reinforcement learning is really the next big thing because imitation learning, in general, overall, it's a supervised learning struggle with generalization. For example, if we do imitation learning for autonomous vehicle and we train the car in Alaska, right? If we take that to New York City, it probably doesn't work well. This is the problem called distribution shift, right? How we can using this, but for reinforcement learning, it has better generalization capability. And for supervised learning, in some sense, it's kind of like an open loop control, right? It's a fixed matching, no feedback. You need an intensive human labeled data set. For reinforcement learning, it's more like a closed loop control. It's more like an adaptive control and the self-generated experience and reward signal. But, we can do a lot of new learning solutions. For example, curriculum learning with our framework, right? We haven't done that yet. In our Nature paper, we only did a very simple, fully connected MLP, this kind of architecture. But there are a lot of new methods we can use, like a curriculum learning, a lot of teacher-student privilege learning. Overall, I think there's a great opportunity to use the same framework, but to apply different learning methods. I think overall, I would the lessons we learned that physical AI is the next frontier. I think in the Icon Center, you guys are already doing this physical AI for a lot of like different very cool applications. If you want to build the best robot, you probably need to design the best hardware and some kind of software, right? And the reinforcement learning really is a new opportunity to control the object. We want the robot to overall to be more autonomous, really make people's life easier. You don't want the doctor to tune the parameter for half an hour, right? That's very labor intensive. And I would say really embrace AI. It really it's called the largest, the latest leverage, right? Has a superpower to enable a lot of work. Learning in simulation can solve many data challenges because for us, it's we synthesize the data, right? Actually in our Nature paper, we only have 1% data. We download it online. We didn't collect any human data. It's downloaded from CMU, some like open library, 1% data. It can be generalized to many scenarios, right? And learning in simulation is model-based because the simulator has a lot of model. The muscle model, musculoskeletal model, it's learning, but it has a model, right? So engineering, the physics is still important, right? Yeah, if you ask me where we are now in terms of medical robotics or physical AI in healthcare, I would say using the smartphone analogy, we are still in the early stage. Despite a lot of great work, I think there's still a lot of opportunity to advance this field through AI and AI learning control optimization. With the Icon faculty or students, we can all work together to make this to the next level. Yeah, okay, thank you so much, yeah.
Thank you very much, Paul, for the great seminar and any questions. I know there are a lot of students.
Great talk. I think it was really cool. I especially love that figure where you have like the pain scale to show the effect how you supervise with that. I have two questions.
Yeah.
First is when it comes to like how feasible is it to help somebody learn like a personalized walking strategy? Like I'm seeing in the case, like say somebody has osteoarthritis and like one part of their articular surface is really thin and we want to avoid that area. So what if, even though we have a generalizable gait cycle, how feasible would it be to teach them something so that they avoid that pain point? That's the first question.
Yeah, I think that's a really important question. So our solution is kind of like a one-size-fits-all, right? So we learned this, it has a really nice generalization capability. So what we are working on is called that part is called sim to real. We were able to create the sim to real gap, right? So to answer your question, I think we are working on real to sim. For example, we can use a smartphone to just capture. Let's say if you walk a couple strides, maybe even 1/2 minute, we can roughly capture the person's gait feature, and we can turn this to animation, to musculoskeletal simulation, and we can customize the controller for that person, right? I think if you are talking about even, I'm talking about the muscular gait level, right? If you are talking about even tissue level, we can probably, actually we have some paper to do this force modeling between this knee joints, right? And we can use maybe medical imaging to look at this geometry. For that part, we did a little bit of work to consider this. But honestly, it's still a little bit open area, a little bit for that part. I think at musculoskeletal level, I think we have some kind of solution. For the tissue level, we are not there yet.
Okay, gotcha. And then my second question, much quicker, is so there's obviously this trade-off between complexity and like efficacy when it comes to your exoskeletons, right? So I was actually wondering, like, the knee has so many degrees of freedom. How common is it for exoskeletons to assist on not just like the flexion and extension? Like, I assume that like the soft exoskeletons are better for that. But
that's really both are great questions. I think for the knee joint, actually more complicated in some sense, more complicated because they are kind of like hip is like a ball joint, kind of like a socket joint. In some sense, I mean, it's not that easy neither, right? But a knee is really unique joint, right? If you look at anatomy, right? So we came up with some like the key feature is we not only assist this central plane, right? Let's say if I walk, this is called a central plane. I don't only assist this, but also through our mechanical design, we ensure we don't affect this kind of abduction motion, right? So this is also very natural motion for the mechanical design. It's a passive joint, it doesn't limit this. I think that there's some group, they did some like, for the knee joint, I think there's no good solution yet. For the hip joint, I know there's some University of Utah, they did a hip exoskeleton for the flexion, this plane, and also abduction, 2-degree freedom to assist this. For the knee joint, I think it's pretty difficult. I don't see any good solution because it needs to be very lightweight, right? My mom wears some like a brace. She said, I don't want to wear this. I think she probably doesn't like our exoskeleton. It's still a little bit heavy, right? So I think for that part, I think a soft suit is maybe a good solution. We're working on this, but for pneumatics, the problem is the force is kind of small and it's not very easy. We made a portable version, but it's still kind of like this large. So we are still maybe in 2 years, we probably have some version that my mom is willing to wear. Yeah.
That's really great to say. Thank you so much.
Yeah, thank you.
Any other questions?
Yeah.
We got a few questions online, and one is trying to ask if could you provide more introduction into your soft transmission, because it might not be mentioned too much in the presentation.
Yeah. So for the you can kind of see from here, right? So we have two kind of software transmission, whether this cable, the second is pneumatics. But I think maybe the most important lesson I learned is the pneumatics is actually transmission, not actuator. Many people consider this soft actuator, they call it actuator. That's actually the transmission part, right? So the true actuator is a pump that really converts electrical energy to mechanical. So for that part, we are working on some solution to try to really improve the pump performance, not only the pneumatics, the software, this inflatable actuator. So that's important, but the true actuator is the pump itself. So really we work on both transmission and the true actuator. Yeah.
And there's another question asking, when you are demonstrating the lifting, the upper body exoskeleton, the person is asking why the brace is on top of the shoulder instead of it, because intuition wise, it might be.
I think that's a good point. Actually, for the human joint, I think for the shoulder axle, the most difficult part is shoulder is also very complicated. It's not like a railroad joint, right? So we have some like a kind of clever mechanism design. It's called a mechanism to minimize misalignment. Because let's say this joint, right, is a simple, is a hinge, right? But this is not a hinge, right? So actually there's this kind of anatomy. I don't know how this anatomy is also very tricky. So we have a paper to be submitted. So there's something kind of very, it's not that you just make you should not make a single linkage. Some people make like a ball joint, like a 3-dot linkage. The problem, as she said, it's getting too complicated, right? So you want to mimic anatomy, just because 3 joint, right? 3-degree freedom here. So actually very difficult. So we have some kind of clever design to make that simple. It's 1-degree freedom. I mean, overall it's 2-degree freedom, right? You can assist this motion and this motion. We can assist it too. But the overall design is very simple. It's we call this under actuated mechanism design solution. Yeah.
Like the actuator was free.
Yeah.
So you also found the basis on rotary, like rotor design, motor design. So I'm thinking like if you have any insight on like the future humanoid actuator design, would that be linear and or
yeah, very good question. So I personally prefer rotary actuator because when you do the linear actuator, you convert from because most human joints are rotary, right? And in the end it's rotary, right? Muscle is linear, but in the end, and this for electrical motor, right? you don't, when you have like from rotary to linear, then to rotary again, this is called like a transmission, right? Any any kind of transmission, you lose the efficiency, right? And making the things, the overall design too complicated, right? So overall, I prefer simple design, right? A simple actuator design, simpler, better. Maybe overall, that's the general idea. But you know, another point I want to say is for human, right? Human itself is a humanoid, right? Each person is a humanoid robot, right? It's a, you know, maybe we are the best humanoid robot ever designed, right? So we really, you know, think about, you know, I think from this perspective, I think Apple has some paper this last year. This is like a human as a humanoid, this kind of paper. I think they, you can go to archive from the Apple humanoid group. They did a little bit of research on this. So I think, you know, you really understand the human is still very difficult and tricky, right? Human behavior, you know, the human physiology sometimes is very counterintuitive. It's not that easy, right? So really, this may be my 2 points. Yeah. Okay.
Me, yeah, I'm very interested in your lecture work, and also like a little bit following up to the previous questions, because in the simulation you use the muscle skeleton model and the policy controlling those model to like mimic human and have a exoskeleton to assistant.
Yeah.
So I will think that the work is somehow try to represent human behavior using the policy plus the exoskeleton model. But because you say you only do reinforcement learning, there's no imitation to human.
My point is when I mentioned the supervised learning, so there's some labs or companies, they only do imitation learning. Only, right? So we do part of the imitation learning, but there's also reinforcement learning, right? So if you only collect 30 people data, it's still kind of limited, right? So, you know, supervised learning is basically like, you know, the Alex had, right? Recognize is that a cat or what kind of animal. So, but it's kind of open loop, right? So that's not, if you add, if after ChatGPT, supervised learning or reinforcement learning, which has higher level autonomy, is a super RL is better, right? So, but you know, RL cannot solve all the problem, but in some sense, overall, it's kind of like inspired. You know, it's kind of learning by experiencing, right? Interaction, right? It's not that we explicitly tell the robot you have to do this, right? So supervised learning is more like for example, when you walk, your knee needs to follow this trajectory, something like that style, right? But that's not it's like a professor teaching students. You don't want them to just copy paste, right? Imitation learning is copy paste, right? And even in AlphaGo, it's not only imitation learning. If AlphaGo is only imitation learning, it cannot beat the Licidon, right? So because they have something like other methods to, you know, they did the imitation learning, also reinforcement learning and Monte Carlo tree search, some three methods together. Only imitation learning, you probably can only match that data set. If you really want to exceed the data set, you need to do some reinforcement learning or even other methods. Yeah. Oh, okay.
In the experiment-free controller learning, when do you know that the controller is safe to deploy?
Oh yeah, very good question. So we have actually several kind of strategy. First, we look at the animation. Right, from the animation, we can tell if the person is walking in a good gesture or pose, right? So we can, you know, you can see if it works or not, right? The second is the muscle effort. We want to see the robot can truly reduce the muscle effort. Because sometimes when I ask my student, does it work? Sometimes people say it works, but you really need to look at not only the animation, also the joint movement. It should reduce the muscle effort, right? The third part is we did some like a T-SNE, the Jeff Hinton, some like T-SNE diagram. We found that underlying the controller, the learning sometimes like a gate dependent. Even we didn't explicitly say this, right? So basically we can construct some like a metrics online, right? To really quantify. In our nature paper, in the supplementary material, we can quantify the how safe. Because if the person is doing some kind of like we did a walking, running, stair climbing with the person that let's say does like a jump. We don't want the robot to assist it because we haven't trained this yet. It probably works, but we're not super confident yet. So this is kind of like a three mechanism to ensure some kind of level of safety, right? The new work that we want to do is we actually can simulate corner cases. It's like an autonomous vehicle. We can let the person fall, right? In the real world, the IRB will not approve. We do the human falling experiments, but that's the benefit of the simulation. We can let the person fall, and then we figure out how to do the gate stability control, right? So a lot of cool stuff there. Yeah. Thank you. Yeah.
Thank you. Okay. We'll stop here, but we are Dr. Chu is free until 4:30 for next week. So
Yeah.
feel free to talk to him, from now and before.
Yeah. Thank you. I'm also looking for PhD students.
Yeah.
If,
So we have many master students,
Yeah.
Feel free to reach out and apply. Thank you very much. And
Yeah.
For the question and seminar.
Thank you.
This is actually one student online asking
Oh.
how to get in touch with you.
Oh, tell me.
Hi, I have one question. Also, my name is Madeline.
Battery. Okay.
Nice to meet you. Actually, it was quite funny. The photos you had, second last professor, Dr. Young, Kim. She was my senior design.
Oh, you had see, I just met her yesterday. Yeah, I went to Chicago. Yeah, your master.
No, so I was in her senior design class. Unfortunately, I graduated in 2020, so I was doing a hip skeleton for her, but because of COVID, we couldn't really do.
Oh, right. That's difficult moment. Yeah.
Yeah. I have a really quick question. I was curious about how long did it take for for your policy to train? I guess from the reinforcement learning, since there's so many parameters.
It's about 8 hours.
Okay.
Yeah, now actually 5 hours because we are getting better GPU. Yeah.
Okay, and that just to clarify, so it was online. It was dating online. All the products
The policy when it's learned, it's fixed. They don't adapt change it anymore online anymore. So we are trying to work on online fine tuning right now. Yeah.
Okay, gotcha. Okay, well, thank you so much.
Yeah.
Actually, real quick question, just in case, are you looking for any postdocs by any chance?
Postdoc is a little bit tricky because but are you undergrad or?
So I'm a PhD student. I'm in my final semester.
Oh, who do you
right
work
now.
with?
I work with Dr. Nira Jain, but
Oh,
I'm
okay.
interested in rehabilitation.
It was I have like a 4 postdoc now, but because current funding, I mean, I got a new grant, but the overall and NYU, the postdoc is very expensive.
Yeah.
The overhead is larger than what I did in North Carolina. So generally, I'm unless the university can sponsor something.
Yeah, that's totally understandable. I just figured I'd ask.
Okay.
But I'll definitely look into the work a lot more. Thank you. So
Okay,
much.
cool. Yeah, thank you. Yeah.
Can we have a question? Using one data set from one person.
Yeah.
If you look at like any random person with some kind of disability, they will have all the same muscle.
Yeah, we only in the nature we only did a healthy people. Yeah, so we are doing this what I said real to same. So we're doing the people with disability and our more products.
But if let's say you take like only one training of a healthy person, that here is not similar to everybody's gait who you're testing.
For healthy people, yeah, I think overall it's not exactly the same, but somehow it generalized very well. So we tried like a study of people, works immediately. Yeah, we didn't see any issue. Yeah. So we don't quite understand, but for RL this is generalization capability.
Yeah, so that's a great talk. Sorry, I just joined the last Q&A section.
Okay, yeah.
So I'm wondering for skeleton, what's the design factors for like motors? Like what kind of factor would it be?
It's for example, in the end we want to make the top high top. Get a high top. So basically one how many pole pairs? Many motors have like maybe 12 pole pair, but in our we have like 18 or 20 something, many pole pair, because that's ideal for high top application.
So maybe in other words, about density?
Yeah, we want to improve the top density, so the pole pair is how many magnetic poles, right? That's one factor, and also the diameter, the thickness. So it's kind of simple, but we have some expert